All right, so we're looking at lesson 1-3 today, which is on exponentials. And exponentials are our fancy way of looking at growth and decay. We're going to look at how do we examine increases or decreases at rates that are nonlinear. So essentially, they're just a nonlinear type of change that is increasing or decreasing. In order to understand exponential growth and decay, we're going to do some warm-up questions in our notes packet for 1-3. So what I want you to do is look at these problems. So this is like the second page. I'll have the first page on there right now because on this page, I gave you a couple adjustments to the lettering to match how you would have learned these formulas last year. So our books use N, we have T. You guys are actually, it might be in the end of the other one notes. Like I think that starts next week. Where I'm pretty sure I made them like week by week. No? I just didn't give you the quick review. We start with this. Okay. I'll look at it. Sometimes I split it up between first. Oh yeah, that's the page. Here's the review that matches that. So easy because I have to like what I have saved is the filter. And also I was like exporting those PDFs and trying to convert it to be functionable in Unified. It's not perfect. All right, so go ahead and just do the quick review at the top of that page. So in the quick review, we are looking to simplify these expressions. It's really a matter of can you use your graphing calculator for those first few to understand? So 5 to the 2/3 becomes 2.924. In here, you want to get really, really good at marking your answers with 3 decimals. So anytime you are doing math work from now on, you are writing down 3 decimals. The reason for that is that's what the AP exam asks for. So you can do 3 decimals on the AP exam. The second part says 4 decimals. On the AP exam, you can either round to 3, truncate at 3, or write 4. So they'll accept 3, 3, and 4. Anything other than that, if it is an answer that has a long decimal and you rate 2, you won't get your credit for it. So we practice in here. Anytime we use a calculator, we want to write 3 decimals, or 4 to be safe, but no fewer than 3. And then 4 through 6, again, just some calculator problems. So if you have x cubed equals 17, then what you're trying to do is find the x value that works. So how do you get rid of something cubed? You take the cube root. So we take the cube root of 17 to get that answer.
Good morning. We would like to have a moment of silence in remembrance of the tragedy of September 11, 2001. On that day.
So during this unit, we're going to look at growth, decay, applications, the number e, and then we're going to look at why those functions have the patterns they have and how they're useful to us. So in calculus, you're required to perform algebraic manipulations with negative exponents as well as fractional exponents. You should know that the definition of a negative exponent then is that n to the negative 1 becomes 1 over n. Negative exponents do not make expressions negative. Negative exponents do not make expressions negative. They create fractions. Typically, expressions in multiple choice answers are written with positive exponents. So you're required from here on out to eliminate negative exponents from any answer. Okay. So fractional exponents create roots. The definitions of these are that if you have n to the a over b, if you have n to the a over b, this can be rewritten as n to the a and the square root of b. So again, this is how you take a fractional exponent and convert it to a root. So this is a fractional exponent converted to a root. When we multiply, we add exponents. So the multiplication to addition says that if you have a to the m times a to the n, that is the same as a to the m plus n. So a to the m times a to the n equals a to the m plus n. This is like at the very bottom of that notes guide, just so you know. Like it says, when we multiply, we add. Bottom of the front page. So this is the rule for multiplication. And then we also have a rule for division. The division says if you have a to the x over a to the y, then that's the same as a to the x minus y. So a to the x over a to the y is the same as a to the x minus y. It's important to note that the base must be the same in order to apply this rule. The base must be the same to apply this rule. If we have a power to a power, that's like a to the m n, then you multiply your m times n. These rules apply to exponentials. So tomorrow we're going to look at the number e. So if you had e to the 3 and 2, then that's the same as e to the 6. All right, so we can simplify and write exponents. Our goal is to put everything with a positive exponent. So we have, for number 1, negative 8x to the negative 2. So we rewrite that as negative 8 over x squared. And number 2, you have negative 5x cubed to the negative 2. Here's a mistake I saw a lot of us make when we were working on these types of problems on our packet. We would write negative 5, and then you do 3 times negative 2. But what we forgot was that that negative 2 not only goes to the x cubed, but to the 5. And again, it's not a negative in terms of its sign, it's just telling me this goes to the denominator. So that's the same as 1 over negative 5 squared x to the 6. And then we clean that up one more time. So you have 1 over 25x to the 6. Everything's in terms of positive exponents, and we've gotten rid of anything that could be simplified. Number 3, you have negative 3 over x to the 4th to the negative 2 power. So anything to a negative exponent distributes in or flips your inside fraction. So I could rewrite that as x to the 4th over negative 3 squared. So essentially what I did was distribute the negative in, which flipped my fraction. Now I'll distribute the square. So again, x to the 4th times 2 gives you x to the 8th, because it's a power to a power. The power also goes to the 3, so that's like negative 3 squared, which is 9. So x to the 8th over 9. Number 4, you have 36 x to the 10 to the 1/2 power. We know that that's the same as the square root of 36 x to the 10, because the 1/2 power represents the square root. But But we also know that the rule tells me the 1/2 distributes into each part. So it's really like 36 to the 1/2 x to the 10 times 1/2. And this is why when we take a square root, we simplify the numbers and divide the exponents by 2. So that becomes 6x to the 5th. And then you need to recall the even, odd rule. So if you have an exponent that is even, and it is multiplied by another even fraction, like a 1/2, 1/4, etc., and your answer becomes out odd. So sometimes instead of writing even this way, you see even this way, and then your answer becomes x to an odd. That x to the odd needs absolute values. So my 6x to the 5th needs absolute values. And the reason for that is, what do you know about any exponent to an even power? Well, any exponent to an even power is going to be positive. So 36x to the 10 is going to be a positive number. That's why we can take the square root. So now, if you have 6x to the 5th, an x to the 5th would allow you to get a negative number, hence the need for the absolute values. So if you have an even exponent inside raised to an even square root, 4th root, 6th root, then you need absolute values. The even, odd rule. This is the same as the cube root. A negative flips it, so you get 1 over 27 x cubed squared. But what's another way I could write that? Well, the order with which we multiply our exponents doesn't matter. So I could also say the 27x cubed to the negative 2/3 is the same as the cube root of 27x cubed to the negative 2 power this way. Why is the second option more helpful than the first? Well, by writing it the second way, I can use the cube roots and the perfect cubes to simplify, then take something to a negative exponent power. So the cube root of 27 is 3. The cube root of x cubed is x. So the negative 2. That means I get 1 over 3x squared, which is the same as 1 over 9x squared. Number 6. We have 16x to the negative 2 over 3/4, or to the 3/4 power. So that's really the same as 16 over x squared to the 3/4 power. And again, I know that the 4th root of 16 is going to simplify nicely. So I'll cube it after I fourth root it. And then down in the denominator, I might cube it first, then simplify it. So sometimes you can flip the order, even just depending on that problem. So I could cube the inside, then fourth root the outside. Really doesn't matter. I could actually also in the denominator, and again, just show you different ways to think, multiply by a fraction. So the fourth root of 16 is 2. 2 cubed is 8. So I get 8 over 2 times 3 is 6. 6 divided by 4 is the same as 3 divided by 2. So I get x to the 3 halves. Okay, number 7. I have x to the 1 half minus x to the negative 2. Be careful. A negative exponent or any exponent can only distribute if the operations inside are multiplying or dividing. This has subtraction. The minute you have an operation like addition or subtraction, we are thinking more FOIL. So this is really like 1 over x to the 1 half minus x squared. So what that means is that whole function is squared. So it's really like 1 over x to the 1 half minus x times x to the 1 half minus x. Which means this becomes 1 over x to the 1 half times x to the 1 half. Well, half times half is a fourth. However, when we are multiplying our variables to powers, we have to use our multiplying rule, which says you add them. So x to the 1 half times x to the 1 half becomes x to the 1. And if you think about it, that's like when we used to say, okay, the square root of 2 times the square root of 2. Well, if you have the same square root times itself, you got 2. So now this was like the square root of x times the square root of x which becomes x. And then you have x times x to the 1 half. So again, adding them together, you get negative x to the 3 halves for your outer. And you're going to get that here as well. That gives us negative 2x to the 3 halves. Negative times a negative is a positive, and x times x is x squared. So we have the square root of 4x squared minus 12x plus 9. 4x squared minus 12x plus 9 is a special quadratic because it is a perfect square trinomial. Because you have a perfect square at the front, perfect square at the back. So it factors as 2x minus 3 times 2x minus 3, or 2x minus 3 squared. And we know that the square root of a square cancels them out. And you get 2x minus 3. Number 9, we have x to the 1/3 times 1/2 x to the negative 1/2 plus x to the 1/2 plus 1 times 1/3 x to the negative 1/3. So looking at the beginning, we're going to distribute them together. So you get 1/2 x, and since I'm multiplying, I add. So my first step is just to distribute and combine all my variables by looking at their exponential powers. The next part is to clean it up. So negative 0.5 plus 1/3 is going to give me a fraction with a base of 6. So you get 1/2 x to the negative 1/6. And then same with here. Technically, these fractions need to have bases of 6. So you multiply the 1/3 by 2. So you get negative 2 6 instead of 1/3. Multiply the 1/2 by 3. So you get 3 6. So you get negative 2 6 plus 3 6. So I get 1/3 x to the 1/6 plus 1/3 x to the negative 2 6. We have to get rid of our negative exponents, which becomes 1 over 2 x to the 1/6 plus 1 x to the 1/6 over 3. So the 3 drops, not the exponent, plus 1 over 3x. And again, you could write 2 6 or 1/3. We're done. Then so you can multiply your front numbers together. So you get negative 2/3 times 8. So when you multiply them together, you end up with 16/3, or negative 16/3 rather. I would drop my fraction so it's no longer negative on my exponent. And then we're going to simplify our numbers. So we'll simplify 8 to the 5/3. So we know that 8 to the 1/3 is the same as 2 cubed to the 1/3. So 8 to the 1/3 is 2. And then you have to take 2 to the 5th. So 2 to the 5th is 32. So we end up with negative 16 over 3 times 32 x to the 5/3. Well, 16 and 32 both divide by 16. So you get 1/2. So you get negative 1. 3 times 2 is 6 x to the 5/3. 11. So here they're different, so you can't group them. So you have the square root of x plus 4 times the square root of x minus 4, because the negative exponent would bring it up. But what's underneath isn't the same, so that is your answer. I guess technically you can multiply them together, but it won't simplify. And 12. This one's extremely important. So this one focuses on getting common fractions. So you have 1 over x plus 1 over y to the negative 1. And then when you simplify that, the problem is that you can't distribute your negative 1 in. So what you have to do is get a common denominator, make it a single inside fraction, and then flip it. So we're going to get y plus x over xy all to the negative 1. Now you flip it and you get xy over x plus y, or y plus x. Good? Lots of exponent practice. So that kind of sums up the remainder of what we're looking at. So for today, tomorrow, the weekend, you have the 1.1 to 1.2 on delta. And that will auto-grade itself. I'll go back and have to maybe check through some things. And then your homework side of this is a 1.3, also on delta. So once you get everything done on delta, you're good. I don't believe we have anything to submit until, like way next week. So you use the remaining class time now to work on that. And that's it.